Log on, tune in, find out. Another good idea from Cambridge.
Visitor's guide to what we think about in experimental design and stochastic simulation. And one thing that's going to be common about all of the talks this morning is that there's going to be a movie or an animation. So this is an example of the type of system that most of the people are talking about might think about simulating. So this is an airline check-in. Oops, not on. Thank you. So this is an airline check-in system. You can see the plane over there in the upper right corner, and passengers are coming in. They're going through security. Some of them are using the automated check-in kiosks. Eventually, they have to have their boarding pass taken. People are picking up baggage and the like. It's a dynamic system. Things are evolving through time. You would do this sort of simulation because you're trying to design this facility to make it efficient so that passengers can quickly claim their tickets, find their luggage, get to their gate, and so on. It's stochastic because there are lots of things in here that are not perfectly predictable. The person who forgets to take the laptop out of their baggage, how many bags people have, when they actually arrive, the overall rate of processing folks. So it evolves over time. There are stochastic components involved. There are things that we can control about the layout and the staffing levels, and we're interested in the overall system performance. Now, the animation is just a convenient way to sell the results. We're, of course, actually interested in estimating various sorts of parameters. So the characteristics of the kinds of systems that people are going to talk about over the next day and a half they are stochastic. So as I said, in this example, the arrival processes, the passenger characteristics, the check-in times, equipment failure, all not totally predictable, and they'll be modeled by some sort of completely specified probability model. Values will be generated from those, what we would call input processes, to drive that dynamic simulation. So the responses, and this is a big difference from what we've mostly heard about the first 2 days, the responses are stochastic. So there is noise on the observations that we get, and if we replicate, we get different results. And in fact, replication turns out to be very important. The systems are dynamic, so these are not static Monte Carlo type of simulations. They are dynamic stochastic processes that evolve over time. In the system I showed you, the arrival rate of passengers is clearly time varying, being greater around the time that flights are going to leave and being lower when there is no flight going. There's queuing interaction of customers contending for service. And in fact, that queuing interaction is a big part of what we deal with in operations research when we're trying to design systems so that they will be efficient. As a result, the outputs can exhibit dependence. They may be non-stationary within the output processes that we would look at a single scenario. So IID data, at least within output processes, is not a tenable assumption in the sort of things that we look at. And there are typically a large number of factors or decision variables or feasible solutions, or a term that's often used, scenarios. Right? They can be discrete valued, continuous valued, or categorical. And often what we want to do is optimize because we're trying to design a system so that it has good performance for whoever it is that is going to be using it. Now, when it comes to experimental design, a big difference is that, although not always, often individual replications are relatively cheap. Right? So we're not talking about 6 hours or 12 hours or 24 hours to get one replication, although you're going to see some exceptions in the first two talks today. But often the replications are cheap. However, we have significant heterogeneous variance across the response space. And in fact, it can be explosive. So service systems like the airline check-in, as you get closer and closer to their capacity, not only do the passenger delays increase substantially, but the variability of passenger delays increase substantially. And so any sort of equal variance assumption across the response space is also not tenable. Sequential design is relatively easy to do because the computer is doing all of the work. We're not talking about clinical trials or something like that. And the things that we deal with in experimental design are the following. the choice of which scenarios to simulate, which settings of the factors that we can control. The choice to add replications to a particular factor setting, or in some cases to simply increase the run length, the amount of time we observe the stochastic process at that setting. And sometimes those two things can be traded off as ways to increase the effort and reduce the variance. The choice to use common random numbers to induce positive dependence across scenarios. When we simulate multiple scenarios of that airline check-in system, we can, and in some cases would like to, drive the simulation of each scenario with the same random processes, the same random numbers, hoping to induce a positive correlation which makes the differences easier to detect. But sometimes that's a bad thing to do. And you'll see examples in the talks that are going to happen over the next day and a half where it can be both good or bad to use common random numbers. So that's part of the experimental design. And we also have a choice in terms of the computation. Do we want to distribute these replications or runs or scenarios across multiple processors, and how do we do that? Individual scenarios distributed, parts of scenarios distributed, in different ways that those can be done. So the things that you're going to hear over the next day or so, we're going to start out by actually seeing something about some large-scale, difficult discrete event stochastic simulations that involve multiple fidelity, multiple model stochastic simulations, and that'll provide a nice introduction to the sorts of things that we simulate. Also this morning, some talks about using Gaussian process metamodels, but to model stochastic simulations and how we would use those metamodels. And finally, a fairly substantial focus on the input uncertainty problem. And part of the reason we picked this as a focus is because that is a problem which is certainly common to both groups that are here, although there's a different emphasis on the two. And we'll have both talks and a panel on that tomorrow. And with that, I'll introduce my colleague Bruce Ankenman, who will chair the session today.